They will respond to audio
Oh,
or
okay,
through
fine.
chat. Okay.
Okay, fine, fine. So, yeah. So let's start on the topic. So, microprocess from single core to multi-core. The way I have organized it is, as ma'am has told, I belong to the electronics department, and I think you are from the computer science department. So we electronics engineers normally approach things through hardware. So I'll be focusing more on the hardware side of multi-core process, how this evolution happened. So starting from single core, how performance started increasing, and how why did we move from single core to multi-core, and once we are in multi-core, I'll just briefly introduce like some a few topics there, like that's more on the architecture side, and what is important in when we are doing multi-core programming. So everything. So uh, uh, I'll be mostly dealing with the basic stuff here. So let's start. I'll start with Moore's law. So how many of you have heard about Moore's law? Have any of you heard about Moore's law? Moore's law? Anyone? You can respond. The chat I won't be able to see. So I have so Sam, ma'am, should I continue? So
Yeah. So I was going. So yeah, Moore's law is that the every 2 years the number of transistors in a microprocessor doubles.
yes. So I hope many of you have heard about Moore's law. So Moore's law has been the driving, what you say, that is what has been driving the evolution of computer or processor technology. But it is not actually a law. It was just a statement or a prediction by Moore that from now onwards, every 2 years, number of transistors in IC, in an integrated circuit, doubles about every 2 years. But if you actually look at it, it has been doubling in 1.5 years, every 1.5 years. So what you have to understand is, so every once in 1.5 years, you are going to have double the number of transistors in your IC. So, and these transistors can be used to build more logic. It can be used to build more memory, etc. Which utilizing this more logic and more memory is what has been driving the improvement in the processor technology. So, in addition to what Moore stated, that is, the number of transistors are increasing every 1.5 or 2 years. The frequency, so if you see what I have here is the frequency on the y-axis and years on the x-axis. So as you can see, the frequency also has been doubling every 2 year or every 1.5. So you
So
have,
excuse me.
yeah.
There's the graph in the slide. It's just the first slide here.
Oh, okay. Sorry. Yeah. So there is some delay, I think. So can you let me know once the second slide has started?
Uh, yes, it hasn't started yet anyways. So
Okay. Is it a delay from my side? Just hold on. Let me just keep my mobile
sure.
with me. Yeah. Today, since it is Saturday and we have we are non working, so I am from home, so I have to connect through the mobile. So how is it now? Is the second slide visible?
Still hasn't changed.
Okay,
It's still the first slide.
so has it gone like, is it full screen even now?
Yes.
Screen mode?
Now it's changed. Yes. Yeah,
Okay, so probably,
it's
but
just
then
a
I want,
slideshow. It's just the
yeah.
it's still in the, it's not in the slideshow mode. It's still in the edit
Yeah,
mode.
yeah,
That's all.
but then if it is not in the slideshow mode, I won't be able to use the pen. Okay, let me
Okay,
just
cool.
see. Let
And now,
me,
anyways,
let's,
we can see that we can see the graph now. Yeah,
yeah, let's, how about it now?
it's it's in the third slide, I guess. It's processor frequency. Yes,
Yeah, it's in
I
the
guess
third slide.
that's the
Yes,
slide.
yes. Yeah, so I'll
Yeah.
probably mention that I'm changing the slides. Okay. Okay, so what we have here is the frequency of the process axis and the years as it progresses along the x-axis. So as you can see, the frequency has also been doubling or increasing every 2 years. So we have twice the number of transistors and twice the frequency. So what happens when the clock frequency increases? So clock frequency increases means the cycle time or the clock period is reducing. It is becoming half. So the time taken to complete some operation is automatically going to half as the frequency increases. So earlier, for example, let's say this is your clock period, and now you have a clock period like this. So earlier, the time taken to complete one operation, if it is single cycle, it took this much time. Now it is going to take only half the time, which means you are going to be able to process more within a given time. So this was a like a, what you say, it's a bonus, or it's a free meal. Like the whoever is constructing the architecture, he doesn't have to do anything. He just have to move from, like, you have some architecture, you move it to a new technology, you can operate the transistors at double the frequency, and you are going to get double the throughput without doing anything on the architecture. The frequency increase, it has there you have to do some minute corrections, but let's forget that. Ideally, this increasing this frequency, increase in frequency was giving you a like free improvement in the throughput or the performance of your processor without doing any architecture changes. So in addition to that, you have the increase in transistors, number of transistors, that is transistors becoming double. So if you utilize that transistors to do some worthwhile work, you can improve your performance more. So performance is like for example, if you have a program, how much time you take to complete the program. So that's a very basic explanation of performance, the processor performance. So if your processor frequency increases, you will be able to complete the the program in less time. So, and that without doing any change in the architecture, that is in the processor architecture. So frequency gives you increase without any change in architecture, and the extra transistors can be used to improve the architecture to gain more increase in performance. Okay, so as I noted, every new generation in silicon technology, the frequency scales by 2 times per generation. Transistors increases 2 times. More transistors and faster transistors. So what you get in every generation is, you have, so every generation is around 1.5. A new generation of silicon process used to come every 1.5 years. So more transistors and faster transistors. Faster transistors means faster execution, but there are more transistors. How do you make use of these more transistors to increase the execution speed? So the frequency increase is giving you increase in execution speed. On top of that, how do you make use of these transistors to increase the execution speed? So one way to express the execution time is to measure the cycles per instruction and then use the frequency. How many cycles are taken for completing an instruction, and what is the cycle time? So the cycle time depends on frequency. Cycle time is going to be inverse of the frequency. You multiply by it with number of cycles per instruction. It will give you the time to complete one instruction. And if you have a program, let's say it has 100 instructions, then you multiply uh, the time for one instruction into 100, you will get the total execution time. So cycles per instruction and frequency can be used to compare the execution time. Okay, so let's start with the very first microprocessor, which was Intel 4004. So that was in 1971. It was used for used in some calculators. Some of the characteristics it uses what is known as 10 micrometer process technology. Basically, the silicon technology which was used, it was called 10 micrometer. So the silicon technology is generally referred to by the transistor gate length, which is expressed in micrometers or nanometers. So at that time, the possible gate length, minimum gate length was 10 micrometers. So in 10 micrometer process, that is the technology used was 10 micrometer. You could the microprocessor had 2300 transistors, just 2300 transistors operating in the range of 400 to 800 kilohertz, 4-bit word size, and some pin package. And this was the architecture. So I hope you have I think you have already studied microprocessor, so you know the basic microprocessor architecture. So you have ALU, which actually just does the computing. Then you have control, which does all the controlling part. Then there are registers. So there are all these registers. There is an accumulator. Then you have instruction register, where the instructions are fetched. Instructions have to be decoded to understand what is the operation. And based on the operation, data will be taken from the registers and given to ALU. And operations output will have to be given back to the memory. And this is the data bus which connects to the memory. So this was the architecture for Intel 4004. So now this was in 10 micrometer. So now let's say in 1972 or 73, you have let's say 5 micrometer process. That is, you have a new process technology in which you can fit more transistors. You can fit double the number of transistors. What will you do to improve this, to use these transistors to improve the performance? So that was the question. So in case of 4004, it was very easy because you had only a word size of 4-bit. That is, each word used in the operations were only 4-bit size. So the easiest thing to do is, instead of using 4-bit word size, you increase it to 8-bit word. So earlier, you had to split all your operations into 4-bit operations. Like if you want to add two 32-bit numbers, you have to split it into 4-bit numbers and add 4-bit numbers repeatedly to get 32-bit addition. But you can increase it to so if you increase the 4-bit word size to 8-bit word size, obviously your execution time of your program is going to be reduced. And you have more transistors to fit this 8-bit. So when you have 8-bit word size, remember that the registers have to be 8-bit, the ALU has to support 8-bit, the accumulator has to have 8-bit, and the data bus has to be 8-bit. So all these increase in bits is going to increase the logic inside the processor. And the new transistors which we got, because we changed from 10 micrometer to 5 micrometer, transistors can be used to accommodate this increase in 8-bit. And that's what Intel did. So they went to 8080, Intel 8080 in 1972. But this was not with 10 micro. They didn't change the technology here, but they could accommodate more transistors. So earlier, if you see, it was 2300. Now they could so this was probably because 4040 was a very initial initial stage of 10 micrometer, where they could fit only 2300, but probably they increased the size of the die or something, so that they could now fit 3500 transistors. These extra transistors they used to have 8-bit word size. So now all the registers are 8-bit. So that was the main difference between 8080 and 4040. So without doing much of a difference in the architecture, they by going from 4-bit to 8-bit, they could improve the performance. At the same time, they could use the newer transistors at. So now the next, there was in between, there was other processors, but once they came to 8085, so here the frequency was, so now I am in the, so this is the sixth slide. So in the sixth slide, 8080, the processor frequency was 800 kilohertz. Once,
Excuse,
yeah.
I'm sorry to interrupt, but it hasn't changed from the third slide yet.
Oh, okay, sorry. So what we will do? Let me just hold on. I think we'll have to. So, what happens if it is not in full screen?
Now it's on the seventh slide. Yes.
So I think we'll go with the not full screen mode, but then I won't be able to use the pen, but that's okay. If you are not able to see the slides, there's no point, right? Okay, so we were in third slide, right? So third slide, I said that talked about processor frequency, and then what are the changes happening with technology? That is, you have more transistors, faster transistors. How do you make use of this faster transistors? So once you come to the first microprocessor, which is, so I'm in fifth slide, so it is visible, right?
Yes, it's in the fifth slide.
Okay.
Yes.
So, okay, so I don't have to follow that. So 4004 means it was in 10 micrometer process, 2300 transistors. 2300 transistors operating at 800 kilohertz, and this was the architecture. So as I said, it contains all those basic units required for a processor: ALU, registers, the instruction register and decoding, the control, and then the data bus to communicate with memory, etc. So this was 4004. When you want to improve the performance, what can you do from here to improve the performance? The most obvious thing was to increase the word size. So in 4004, they were having only 4-bit words. Now if you increase it to 8 bits, obviously you are going to get improvement in the performance. Like as I said, 32-bit addition now will happen in less number of instructions. Using less number of instructions, you can add 32 bits. In if the word size is 4, then 32-bit instruction will you have to 32-bit addition. A 32-bit word has to be split into multiple 4-bit words and then add and accommodate for the carry, etc. But if you have 8-bit word size, you have to divide it. The number of splits reduces, so number of instructions reduces, your performance improves. And that is what they did in 8080. So in 8080, the process didn't change, that is, the technology didn't change, but they could accommodate more transistors. They used those transistors to have 8-bit words, and these 8-bit words were so if you see all these registers, the accumulator, ALU, etc., all of them were changed to support 8-bit operations. The data bus also was increased so that you can support 8-bit words, which improves the performance. So moving from 8080 to 8085, so this was 10 micrometer. So in 8085, they were using 3 micrometer, and the frequency, if you see, it is 500 to 800 kilohertz. So less than 1 megahertz for 8080, but for 8085, it is 6 megahertz. So you have around 6 times increase in speed. This is not just the next technology, because I have skipped some in between processes. So this 8080 was in 72, 8085 is in 76. So the major changes here is one, the frequency increase. So this increase in frequency is obviously going to give you faster performance. Then they have instead of having 8-bit data and address bus, now they have 16-bit address bus. And in order to support 16-bit address bus, they need address latch, decoder, etc., which you might have studied in 8085 architecture. So those are the major changes from 8080. So from here, now they have 16-bit addresses. So 16-bit addresses means you can, your memory, the size of the memory which is supported is increased, but then they are using the same address bus for data bus. So you need address latch, etc., logic for that, etc., some multiplexers, and all these extra logic can be implemented using the newer transistor. So instead of 3500 transistors, this has 6500 transistors. So I won't talk further about the number of transistors, technology, etc. But what you can see is this increase in frequency, it gives improved performance. This increase in transistors, if you make use of these transistors, you can improve the performance. And this was what has been followed. Okay, so now let's look at the execution of an instruction. So what are the various stages of an instruction execution? So fetch. So what do you do in fetch? What is done in fetch, instruction fetch? We use the program counter to fetch the next instruction from instruction memory. In decode, so the coming instruction will be decoded to understand what it has to do. Then the instruction will have some operands which need to be fetched from memory. So that is the next stage. Then you execute, that is, if what is your operation? Yes. Yeah. Once you fetch the operands, you use these operands for some operations, like let's say add or subtract or whatever. That is the execute stage. And finally, the output is generated. The generated output is returned back. So these are the basic, this is a basic instruction stages in the processor, like in the instruction execution cycle. So the way 8085 etc. work, all these 5 stages, they have to be either completed in one cycle. That is, you start the fetch and then write back the data. All of them have to be completed in one cycle, or you need multiple cycles to complete an instruction. So if you want to complete one instruction in a cycle, uh, you need all the stages has to be completed in one cycle. Otherwise, multiple cycles have to be used. So what is the difference between these two? So let's do one exercise. Let's assume each of these stages takes 100 nanoseconds to complete. So each of these stages takes 100 nanoseconds to complete. So what will be the execution time for one instruction then? If you have 5 stages and each stage takes 100 nanosecond, and we need one instruction to be completed in one cycle, how much time is taken for the completion of one instruction? We have one instruction to be completed in one cycle. Each stage is going to take 100 nanosecond to complete. So what is the total time taken to complete an instruction? Can anyone answer that? Is the question clear? So an instruction, it has to go through all these stages for it to complete. And we say that each instruction takes one cycle to complete. Okay. And each stage takes 100 nanosecond time. So 5 stages means 500 nanosecond is required to complete the instruction of execution. So 500 nanosecond is taken to complete the execution. And if you want all the operations to be completed in a cycle, it means that the cycle has to be 500 nanosecond wide. Okay. If you want one cycle per instruction, you need each cycle to be 500 nanosecond, which means your frequency has to be inverse of 500 nanosecond. That is, if these are the delays of the various stages, then you can complete the operation. If you want to complete the operation in one cycle, that one cycle has to be 500 nanosecond, which means the operating frequency has to be 500 nanosecond is, I think, 2 megahertz. So you need that operating. So your operating frequency is 2 megahertz if you want the operations to be completed in one cycle. Or you can use 5 cycles to complete the operation. That is another option. Your cycle time you keep at 100 nanosecond, but take 5 cycles to complete. So these two options are there. But whatever be the option, it takes 500 nanosecond to complete the entire operation. And let's look at this. So let's assume that we are taking multiple cycles to complete the operation. Okay, so let's say the first instruction has come. So here we have a 80386 processor which has 6 stages. So I1 means it is the first instruction which is processed. I2 means it is the second instruction which is processed. And we are allowing multiple cycles for an instruction to complete. Okay, so if you see instruction 1, it reaches the first stage S1, which is probably instruction fetch. After completion of instruction fetch in one cycle, in the next cycle, it moves to the second stage. In the second stage, again, it might be instruction decode. Then in next cycle moves to the third stage, maybe execute. In the fourth stage, fifth stage, sixth stage. So total 6 cycles will be required to complete the first stage. So once the 6 cycles are completed and the first instruction is complete, execution is complete, you move to the next instruction. So you bring the next instruction, takes another 6 cycles to complete. But then the problem here is, if you see, each of these stages will be, we see only one cycle per every 6 cycle. Out of every 6 cycle, only one cycle is, the stages are utilized only once in every 6 cycles, which means all the other time it is just lying there. And you need 6 cycles to complete the instructions. So, which means your execution time will be time period into 6. So your execution time is in more, but your resources are just lying there idle. How can we avoid this wastage? So I think you might have studied what is the way to avoid this wastage. Anyone has a clue how to avoid this wastage? How can we utilize these stages more efficiently so that our execution time is reduced? Anyone has a clue? So come on, one of you respond. Okay, so the solution for this is what is known as pipelining. Okay, I think you would have studied pipelining. So basically, what is important is when I1 is executing or is in stage 2, we can have I2 at stage 1. Okay, so when I1 is in instruction fetch, so the instruction decode, that is, the first instruction is decoded. At the same time, in parallel, we can fetch the second instruction. When the first instruction move to execute, we can move the second instruction to instruction decode. So if you do like that, then you can, so you have the first instruction, it is instruction fetch. So this is the instructions, this is the cycles: instruction fetch, decode, execute, and write back, or operand fetch, execute, and write back. In the second cycle, you start instruction fetch for the second instruction, then it goes on like that. And now if you see, you have instruction decode and instruction fetch both happening in parallel. Here you have operand fetch, instruction decode, instruction fetch happening in parallel. Here we have all four of them happening in parallel. So this concept is called pipelining. So pipelining. So what you do is you have all these stages. You introduce buffers or registers in or flip-flops in between these stages so that when one stage is completed and data moves to the next stage, the previous stage can operate on a different data. So as you know, registers or flip-flops, they will sample data only during the clock edges. Whatever happens in between the clock edges, nothing happens. Only during clock edges, data will be moving from one stage to the other stage. So for example, the first instruction, completed instruction fetch, then the clock edge comes, the fetched instruction is moving to instruction decode. So now whatever happens to instruction fetch, it won't affect instruction decode until the next clock cycle. So by introducing flip-flops or registers, you can introduce pipelining. And this concept of using pipelining is possible because we have what is known as instruction level parallelism. So programs have instruction level parallelism whereby you can actually simultaneously process multiple instructions. Okay, when one of the instruction is in decode, you can fetch the previous next instruction. When the first instruction moves to fetch, second instruction can be decoded, and the third instruction can be fetched, and you can go on like that. Okay, but so now how will the time change? So now if you see here, you needed 500 nanosecond to complete the one instruction. And if you assume each stage has 100 nanosecond delay, when we pipeline also, each instruction needs 500 nanosecond to complete. Each instruction still needs 500 nanosecond to complete. But you are starting the next instruction immediately. So after 100 nanosecond, you are starting the next instruction. So once the first instruction reaches write back, then every cycle you are going to get a write back for the next succeeding instructions. So the first cycle you give instruction fetch. After 6 cycle, you get the result. In the second cycle, you give for the second instruction. 7th cycle, you get the output for the second. So 8th cycle, you will get for the third. So like that, you are going to get results in every cycle. So the instruction, although each instruction takes 6 cycles to complete, every cycle you are going to complete, means you are going to get the result from one instruction because of pipeline, which means your execution time in principle can become 1/6 of the actual execution time. Okay, but there are issues. It is not possible to perfectly get pipeline working for realistic programs. So that is because there is what are known as hazards. Okay, so there are different types of hazards. One of the hazard is known as resource hazard. Okay, a resource hazard means, for example, suppose this operand fetch. So we are fetching the operands from memory. So the fetching the operand may not complete in one cycle because memory is away from the processor. You need more time to fetch the data, which means it might take 3 cycles. So let's assume if the fetch takes 3 cycles, but these stages take only one cycle. That means once the second instructions, so the first instruction fetch happened immediately because probably the first instructions operands are in the registers, but the second instructions operands are in the memory, let's assume, and it takes 3 cycles to complete. Once I2 completes OF, then only I3 can move into OF. Okay, so I2 is in OF for 3 cycles. So until I2 completes operation in OF, you can't move I3 to OF, which means I3 has to remain in instruction decode for the 3 cycles. At the same time, only if I3 moves from instruction decode to operand fetch, you can have I4, which means I4 is now stuck in instruction fetch. So earlier, if this was not the case, we could have got write back in every cycle. But now, after the write back of the first instruction, you will get the next write backs only after 3 cycles. So if there was no if operand fetch happened in one cycle, we could have got 4 write backs in 4 cycles. Now we are getting 4 write backs in 7 cycles. So here, one write back here, then after 3 cycles, another write back. So 1 plus 3, 4, 5, 6. So 6 cycles are needed to get the write back. In the other case, we needed only 4 cycles. So this is because some of these resources, for example, here it was an operand fetch. So the operand fetch resource is busy. Because it is busy, the subsequent instruction cannot proceed. So another reason for this type of hazard is, for example, let's say you have multiplication operation. So an instruction which has to do multiplication is generally slower than addition or other logic operations. It might take multiple cycles to complete multiplication, or maybe if there is division supported, it might take multiple cycles. So unless the division is completed, maybe the previous instructions cannot go. So this type of hazard is known as resource hazard. So you are having a obstruction in the pipeline because let's look at another hazard. So let's look at this instructions. So you have an instruction add R1 and R2. So this means that you have to add R1 and R2 and write the output to the R1. The second instruction is subtract R3 from R1. So R1 plus R2 return to R1, R3 plus R3 minus R1, which has to be executed. So if you see here, you have to write the result to R1, and that has to be used to read from to do subtraction. So write, if you know, it happens only in the write back stage, but execute. So the addition or subtraction operation happens in the instruction execute stage. So here there is add and subtract. Let's say instruction 1 is add, instruction 2 is subtract. So only after add completes write back, so and the data is written to the register R1, I2, which is the subtract, can proceed. So the add has to complete the execution before subtract can move from instruction operand fetch, instruction decode to operand fetch, because operand has to be fetched from R1, but that R1 hasn't got the operand. R1 will get the operand only if add instruction write back the data to R1. So this type of hazard is known as a data hazard. So you have to fetch. So this is for add. So for add, you fetch, decode, you get the data from the register, operate in the ALU and write back. For subtract, you fetch the instruction, you decode. When you decode, you find that it needs R1, and R1 has to be obtained from previous instruction. So R1 will get the data, correct data, only after write back here. So you are stopping the execution of the subtract till you get the data at the R1. So you are stalling, you are forcing the instruction execution to stop. Means you are waiting in decode until the data is available in R1 to write back, and then taking it and proceeding. So now again, this type of hazard is known as a data hazard. And this is very common in programs, right? You always have dependencies. So these are because of dependencies. You calculate something, use that value for another calculation. That is very common. And because of each of these dependencies, there will be hazards. And whenever there is a hazard, you have to stall the execution. And whenever there is a stall, so for example, here there is a stall, which means the ALU and the write back stage are not utilized in this, or the reg and ALU stages are not utilized here. And even the fetch decode, all the previous stages are not used here. So, which again reduces your performance, your throughput. So, if there was no stall, you would have got result in 2 cycles, but now the result will be available only after 1 plus 3, fourth cycle. So this is data hazard. Now there is a third type of hazard, which is known as control hazard. For example, there is branch on 0, R1 and target. So depending on the value of R1, if it is 0, go to the target address, otherwise continue. Okay, so this means that this is like a if loop. So if R1 is 0, you go to target, otherwise you continue. So now what happens is uh, when, only after executing this, we know whether to go to this or not. Because branch on 0, R1 target, which means if R1's data is 0, if the data in R1 is 0, you have to go to a different address. If R1's data is not 0, you have to continue with that. So in our normal pipeline, you first fetch this. In the second cycle, you are fetching this. But you don't know whether to fetch this or you need to fetch some other instruction from the target address. Target is an address which is like somewhere else, where if it is branch, you have to go to target and execute from there. So you don't know. Only after the completion of the branch instruction, you will know whether to continue with that or whether to go to the target address. So because of that, what do? You wait till branch instruction to be complete and then only execute. So you wait till the branch instruction is complete. So for example, here the target is some other place where it is add. So depending on the value which you get from the branch instruction, you wait till that and then only start fetching. So then only you start fetching. So if it is 0, you fetch this target, the instruction from the target. If it is not 0, you fetch this instruction. So if the output from the branch instruction is 0, it means, or if the branch instruction indicates that you have to fetch from this target, then you fetch the instruction from the target address, otherwise you fetch from there. So you need to wait these many cycles before fetching the next instruction, which means again cycles are wasted, resources are wasted. So you are going to take more cycles to complete the execution. So this is a third type of hazard. So you introduce pipelining. So I said that you can introduce pipelining. So introducing pipelining increases your increases your performance, decreases your execution time, and we need more transistors to introduce pipelining, and which we have with every improvement in technology. But just by introducing pipelining is not sufficient because of these hazards. So because of these hazards, it's not possible. It's not you can't just introduce pipelining. If you introduce pipelining, these hazards will make sure that you don't get the expected improvement in performance. So you have to address these hazards also. There are various techniques used. So we will look at one or two. For example, the case of data hazards. Okay. So what is data hazard? Data hazard is because of dependency between instructions. So here the subtract has to get data from add, the output of add before subtract and forward. So and sub add will complete the means give the data only after the write back stage as per our earlier execution. So what you do? You will earlier architecture, as per our earlier architecture, add will give data only after write back. So you will wait until write back before reading the operand for subtract. But if you have an option, so where do we get the output of add? The output of add will be computed in the ALU. That is in this stage you get, so after this stage is completed, you get the output of add. So this is add instructions execution. The add, so R1 and R2 data is fetched here, and that is added in the ALU, and the output data is written to R1 here. So you are actually getting the output data here, and then you are writing into a register, and in the next instruction you are reading that in this side. Okay. Instead, if there is a provision to directly give data from ALU to the register stage, ALU output, instead of writing it back to the main register and then fetching it to the register, instead, if there is a provision to give the output of ALU directly to the reg stage without actually reading from the registers, then you can save one cycle. So if you see here, you need to wait 2 cycles before proceeding. But if this option is there, you can reduce 1 cycle, you can save 1 cycle, which means you can improve the throughput. But introducing this logic into the architecture again will require more logic. But we have more transistors. So whenever a new generation comes up, you have more transistors. So the architecture experts, they will come up with all these sophisticated forwarding architectures, etc. So they will improve the architecture to use these transistors to implement this forwarding. So similarly, there can be forwarding between different stages also. So here we have just mentioned from ALU to register. So there can be other options also. So all these options improve your performance. And how are we able to implement these options or this logic? Because we have more transistors. So when you move from one generation to another generation, you get more transistors. You use these transistors to implement this logic so that your performance is improved. Now, the next is, how do we handle control hazard? So control hazard is when there is branches, you have to wait till the branched instruction is completed before moving to the next one. So one way to do that is, it is a software way where not just software. So it is to rearrange the instructions. For example, consider this: you have an add, then you branch, then you do subtract. Okay, so you have add instruction, then you have a branch instruction, and if branch is taken, you have to go to a different address. But then if the branch is not taken, you have to continue. So now what you can do is, you first, so as per this program, you do the branch only after completing the addition. But this branch and add, if they are independent, that is, the branch instruction is independent of the add instruction, you can move the add instruction after the branch. So add here, it adds R3 and R4 and writes to R2. Okay, suppose the branch is not dependent on R2, it means you can complete branch first and then do add. It doesn't matter because branch is not dependent on the output of add. If that is the case, you can first do branch and then add. And now what happens? We know that add has to be executed irrespective of the branch, whether it is branching to the target or whether it is continuing, add has to be executed because add was a previous instruction. So now you first do branch, then you do add. Add can be given immediately because anyway it has to be executed, and then only you wait. So you can wait after introducing add. So what happened earlier? First we introduced add, then we introduced branch. So first we fetch add, then we fetch branch, then we wait till branch is complete before sub is fetched. But now instead of that, first you fetch branch, start executing branch, next cycle you start add, and you don't introduce sub. You will introduce sub only after branch is complete. But instead of spending 3 cycles between the branch and the subtract the next instruction, this one cycle can be used to execute the add. So add will be executed after the branch. So this saves one cycle. So this is known as delayed branch. So all these slots between the branch instructions are called delayed slots. You analyze your program and see whether any instructions which are independent of the branch can be moved to these slots. You move those, then you will fill these slots and save some. So save some execution time. So this is one way. Okay, this is one way to overcome the problem with branch or a control hazard. Another way is you try to predict the output of branch. That is, you have this branch instruction. You assume that okay, branch is always going to continue to sub, and you start executing sub. If so, you fetched the branch instruction. In the next cycle, you fetch the add instruction. For example, here you fetch the add instruction and you continue executing add. When the branch instruction is completed, you will come to know whether your the next instruction is add or not. So if the next instruction is add, you have no problem. But if the next instruction is the target, then whatever you have started with the add is wrong. So you do what is known as flush. So I'll repeat. So you have this branch instruction. In branch instruction, you fetch the instruction, execute, and based on the result, you have to either execute this add or the target add. So now, in order to save some time, instead of waiting for the branch to complete, you immediately start the next add. If the next instruction is add itself, you have no problem. But if the next instruction as per the branch is target, then you have a problem because you have unnecessarily executed this, which might affect some output, and you have not executed this. If that means if you are predicting that the branch instruction, the next instruction after branch is add. If the prediction is correct, you continue. If the prediction is wrong, you do what is known as flush. Flush means whatever impact this add instruction has introduced, that is whatever changes this add instruction has introduced, all of them are flushed out, and then the target add is introduced. So if your prediction is correct, you save lots of cycle. If your prediction is wrong, actually you are wasting additional cycles for flushing. So this is the basic idea of prediction. So there are different prediction strategies. Fixed prediction, for example, you always take the never taken branch. So that is like I mentioned, you always take the next branch. If it is always next, if the next instruction is complete, it continues. But if your prediction is wrong, you have in problem. But then, for example, consider loops. In loops, so if you remember, if you remember what happens in loops, you reach the end of the loop, you are always going to jump. You are going to the target, so you can't continue. So the branch never taken is not a good strategy for loop. So that is fixed prediction. Then you have static prediction, where for loops you will have some type. For conditional, that is for if statements, you have some type. So for if statement, you always take the not taken branch. For loops, you always take the taken branch, something like that. Again, it is static. Static logic. Fixed also needs more logic. This prediction is going to take more logic. You have to implement flash. You have to implement this how to like compare the results, etc. All these needs more logic, which can be implemented by the transistors. Or you can use dynamic prediction, where you use the prediction results of earlier cases. So, for example, earlier I predicted that go to the taken branch. Okay, so I will go to the predicted taken branch now also. Something like that, some logic like that you implement as a state machine, which makes use of the history of your program to improve your prediction, again, which needs more logic. So these are some examples by which you can you can improve your performance by making use of these additional transistors, which has been happening for over the years. So we started with a non-pipelined architecture. We introduced pipelining. When we introduced pipelining, these hazards came into picture. Then we implemented logics to overcome this hazard. When we got more and more transistors, we introduced more and more logic. So that has what has been happening over the years. So we started with a single cycle data path where this is a single cycle, everything completes in one cycle. There is no registers between the stages. So here you have instruction memory, instruction fetch, and decode happens here. Then you have fetching, operand fetch happening here. Then you have execute happening here. Here you have memory accessing data from memory, and you are writing back to the registers. So all these, this is a single cycle data path. Everything happens in one cycle. So the delay of all these stages adds up to your total delay of instruction. From there, we move to pipelined data path where we introduce these registers. So these rectangular blocks between these stages are now registers, and then you need additional registers, etc. So once you introduce pipelining, you need lots of additional registers. So all these registers can be, registers means it's flip-flop. So all these flip-flops can be implemented using the additional logic. So from pipelined data path, we also introduced forwarding. So you have something called a forwarding unit, which forwards data from various stages to the previous stages, so that data hazards can be reduced. So you have more logic there. Then you have branch prediction, where you predict the branches. You have some detection unit which detects whether your prediction is correct, and based on that you do flushing, all those additional logic for that. So all these increased logic can be, so this is how, this is what architecture designers were doing over the years to make use of these increased transistors, availability of transistors, to improve the performance, in addition to the improvement in performance obtained by the frequency. Frequency increase always give you improvement in performance. In addition, you use these transistors to implement this logic to improve the performance. Okay, so this was one way. Another way is you have memory. So your CPU has to access data from the memory. So memory, there are different memory technologies, SRAM and DRAM. SRAM is a static RAM, DRAM is dynamic RAM. SRAM is more dense, more costlier, faster. DRAM is cheaper, slower. Okay, so SRAM is faster but expensive. DRAM is cheaper, but it is slow. So the problem the serious frequency increase is memory technologies. The pink line is for SRAM, the green line is for DRAM, and this is for disk, hard disk. So if you see, the processor's speed increases very fast, but the memory's speed is not increasing that fast. So the computations become faster, but the memories are not getting fast enough. So if you are using DRAM, you fetch the data. Now in the next generation, your computation, so you, for example, you use DRAM to fetch the data. In one technology, one generation, you take say 100 cycles to fetch the data. So now you move to the next generation, in which case your cycle time becomes half. Okay, 100 cycles the memory takes, but in the new generation, the cycle time becomes half, but the memory speed doesn't change, which means you now need 200 of this reduced cycle time, 200 cycles to fetch the data. So the CPU cycle time reduces, and if the memory cycle time doesn't change, memory's access time doesn't change, you need more CPU cycles to access the data. So more cycles means your data coming from the memory is taking more cycles, uh, your execution is going to be slower. You need to wait till the data comes from the memory to continue the execution. So as the CPUs become faster, the memories are not becoming faster. So how do you address this problem? You have what is known as cache, or you use a memory hierarchy. So where you have registers, you have cache, on chip cache, off chip cache, you have main memory, etc. And you use what is known as locality. You have every program, generally programs have data spatial locality and temporal locality. Temporal locality means there is a chance that some data you have used will be reused again immediately. Then spatial locality means you use some data. It will be like data closer to that will be. So for example, you have an array, you use zeroth element of the array. There is a high chance that you are going to use first element also. So instead of fetching 0 alone, you fetch 1, keep it closer to the processor. You can. So you have some array in DRAM with has 100 elements. Then you wanted, say, 0th element for some operation. So instead of fetching 0 alone, you fetch, say, 10 elements, keep it very near the processor. So this is very close to the processor. This is away from the processor. So from here to here, the access time increases. So more time is required to fetch data from these stages. So if you have 100 element array, instead of fetching only one data, you fetch 10 data, keep it near the processor. Because of spatial locality, most probably the other 10 data also will be used, which saves time. Similarly, you keep that 10 data for some time. There is a high chance that those 10 data are going to be used again, which is temporal locality. So temporal locality and spatial locality can be utilized by implementing cache. Cache is SRAM memory. In most of the time, cache you can include cache inside the processor itself, which makes it very fast. And since you have more transistors in your chip, you can increase your SRAM size from generation to generation. The size of the cache or the capacity of the cache increase means your program can become faster. So that is another way to utilize the memory, utilize the increase in transistors. So you improve logic, you increase memory, uh, you can improve the performance. So with that, we'll come to the end of sequential processors. So I have just touched upon very basic examples of utilizing the logic. So there are other techniques like superscalar, VLIW, etc., where more logic is used to improve the performance further. You can have multiple ALUs, you can have ALU, floating point unit, etc. You can have you can fetch multiple instructions and execute multiple instructions in parallel. So all those options are there in a sequential processor, which needs more complicated logic to be implemented, and that has been done over the years. Okay, so now I said that as you go from one technology generation to the next, frequency increases, number of transistors increases. But there is an issue. So, sorry, uh, there is a problem. So, sorry for this slide. So, as the we have been looking only from a performance point of view, but there is a power dissipation or heat power dissipation point of view also. Power dissipation can be generally expressed as the capacitance. So transistors power dissipation, it depends on the capacitance, the power supply voltage, and the frequency of operation. A transistor acting as a gate, its power can be expressed as the capacitance of the transistor, the power supply voltage, and the frequency of operation. So now what happens when we go from one generation to another generation, I said that frequency doubles. When you move from one generation to another, the frequency is going to double. When the frequency doubles, what happened to power? The power is going to double. Another thing is, I said, as you move from one generation to another, the number of transistors are increasing. Number of transistors increasing means the capacitance of the transistors are also increasing. So capacitance doubles, frequency doubles, which means power dissipation should become 4 times. But that never happens because as you move from one generation to another generation, you reduces VDD. The power supply voltage gets reduced. So if you know the gates which you use in your digital lab, circuits lab, logic circuits lab, they will have some power supply of 3.3 volt or 5 volt, etc. But if you look at the microprocessors which we have in our laptop or mobile, etc., they will have a power supply of only 1 volt or something. Okay, so there will be power voltages like 3.3, etc., for interfacing, but the processor's core voltage will be now 1 volt compared to the older gates which have this 3 volt and 5 volt, etc. That is because the gates which you use in your labs, they are generally from the older generation which used 3.3, etc. And now we have to have that interface voltages to be kept, so we can't reduce that. So older technologies had higher power supply voltages. As you move from one technology generation to the next, you are reducing the power supply and voltage. The voltage is reduced half means the power reduces by 1 by 4. So frequency increases by 2, capacitance increases by 2, VDD reduces by 2, so that power dissipation remains same. So what this means is, when you move from one generation to another generation, so for example, you have 100 transistors operating at 1 megahertz. You go to the next, you have 200 transistors operating at 2 megahertz. But because power supply has been reduced, the power dissipation of 100 transistors at 100 megahertz and 200 transistors at 200 megahertz remains the same. And this is very important because, as you know, what happens if the power supply, if the power dissipation increases? Increase in power dissipation results in heat getting generated. Heat getting generated means your IC becomes hot, the temperature increases, and finally it can destroy the IC itself. You can there will be failure in the IC itself. Okay, so you can't allow that. So power dissipation remaining constant was a feature of all these improvement in technology earlier. And this type of scaling is known as Dennard scaling. So VDD is scaled down as size is, sorry, this is an error, a mistake, size is increased. So as size increases, VDD is scaled down, which is known as Dennard scaling. And Dennard scaling ensured that power dissipation remains constant. But what happened is, by 2005, we reached a case where VDD was about 1 volt. So VDD was 10 volt, 5 volt, 2.5, 1.8, 1.3, and finally we reached 1 volt. And you can't reduce VDD further because of various issues. You can't reduce VDD. So now you go to the next generation, you have 2 times transistors, 2 times frequency, but you can't reduce VDD. What happens? VDD you are not reducing, CL increased, FSW increased, power dissipation is going to increase. So power dissipation increases means more heat generated, and you have to remove this heat by using cooling techniques. But cooling technology is not that good enough to remove all the heat. So you can't allow transistors to get heated up. You can't reduce the power supply. You can improve the cooling techniques. Then the only way to now keep the power supply constant is to keep the FSW constant. That is, you don't increase the frequency from one generation to another. As you move from one generation to the another, the technology gives you the option to increase the frequency, but we don't increase the frequency, because if we increase the frequency, power dissipation increases. So that is the reason why, if you have noticed, the clock frequency earlier, when we were in our BTech days, every processor will give you an increased frequency, clock frequency, which was a big deal. But later on, around 2005-ish, the clock frequency stalled at around 2 to 3 kilohertz, somewhere in between 2 to 3 kilohertz. And now no one claims to have a higher clock frequencies, like I am reaching 10 gigahertz. No one says that. So that is because if you increase the frequency, power dissipation increase, you have to provide technology to cool that down. And that is not possible. So this era is known as the post-Dennard scaling era, where your power supply voltage is not reduced, so you can't operate your devices at high frequency. So what happened? So until 2005, architecture guys, or the so companies like Intel, they were getting free meal, because frequency is increasing. You are obviously going to get increased performance. But now, after 2005, clock frequency doesn't increase, so you are not going to get this increased performance. But transistors are still increasing. Frequency has remained constant, but Moore's law is still valid. Transistors are still increasing. So you have more transistors, but you can't increase the speed. How do you utilize these transistors to compensate for constant frequency? So all the improvements which we mentioned earlier with sequential processors, most of them have become very complicated, and by 2005 you can't improve further. Any further improvement will give you only very small improvement in performance. So that was not an option. The other option was to utilize what is known as thread level parallelism. So thread level parallelism means, in your processor, it is not just one program you are running, you might be running multiple programs. In a sequential programs, all these programs or tasks have to be executed sequentially. Instead, you can have multiple cores in which you execute these threads. Assuming these threads are independent, you can execute these threads in parallel and reduce the execution time. So instead of having a single core in your IC, or earlier you had only one core, your frequency was increasing. Now you have multiple cores all operating at the same frequency. So moving from one generation to another, you can increase the number of cores, keeping the frequency constant, and still gain some improvement in performance. And this was the era of multi-core processors. So basically, you are compensating for the reduced frequency or the stalling of frequency by increasing the number of cores. And there are two different ways in which multi-core processors, two different configurations. So this configuration is known as a shared memory configuration. This is known as a distributed memory configuration. So in shared memory, so you have these 4 cores, all of them sharing a single memory. So all these cores can read and write from this memory. Whatever this CPU writes, another CPU can read. On the other hand, in distributed memory processors, the memory is tied to the CPU, and this CPU cannot read or write from this memory directly. Instead, the data has to be sent between these processors. Here, this CPU writes, this CPU can read. Here, if data has to move from here to here, data has to be sent from here to here. So there are ways to have distributed memory and still share the data, but that that we don't know. So instead, assume that data, if this CPU has to read data written by this CPU, it has to be sent explicitly. So this is distributed memory. This is shared memory. So the definition is not very completely correct, but for ease of understanding, I am just making this. So shared memory processor. So let's see how we can utilize this and what are the issues involved with this multi-core processors. Very basic issues. Okay. So consider this operation. So you have to have a vector dot product. That is, you have this one vector which has to be multiplied by the other vector and find the dot product. So what is dot product? You multiply individual elements and add up all the results, you get the final output. So you have a 4-element vector multiplied by a 4-element vector. Finally, you have to get a scalar value. So, and we are going to utilize this 4-core processor. How do we do that? So one way to do that is, so you have this element 1 here. So this CPU will compute 1 into 5. Second CPU will compute 2 into 6. Third CPU will compute 3 into 7. And fourth CPU will complete 4 into 8. So the 4 products are going to be computed by the 4 CPUs. And then once all the outputs are results are generated, all of them are returned to the memory. And after that, one of the CPU will read all the results from other CPU, add them up to get the final value. So the products have to be added up to get the final value. So one CPU, so the program will be written like such that each CPU will compute will fetch the data from one vector, fetch the data from another vector, multiply it, write the data to the memory, and then after all the CPUs have completed, one of the CPU will read the data written by all the 3 CPUs, add it up, final result will be written. Okay, so this is how, so earlier, if there was only one CPU, that CPU had to do this sequentially. Read 1, read 5, multiply. Read 2, read 6, multiply. Read 3, read 7, multiply. Read 4, read 8, multiply. Then add. All the operations had to be done by a single CPU. Now, 4 CPUs are sharing this. Okay, so so this is what happens. You distribute the pair of elements in each core, multiply in parallel, store the product in memory, and calculate the sum in one core. So this is how you can utilize the multiple cores too. So now what happened? The multiplications are all of them are happening in parallel. Only the addition takes extra time. The multiplications are done in parallel. So, so let's do one exercise. If memory read and write is one cycle, so it takes one cycle to read from memory, one cycle to write from memory, and it takes 3 cycles to multiply. So each multiplication operation takes 3 cycles, and each add operation takes 2 cycles. And your frequency is 1 gigahertz. So can you calculate the execution time? So let's forget the frequency for now. Can you calculate the execution time in terms of number of cycles? How many cycles are required to complete this operation? Memory read and write. So in order to read from memory, 1 cycle, write to memory, 1 cycle. Multiply 3 cycles, add 2 cycles. How many cycles are required in this 4-core processor to complete this? And how do you do that? You first fetch, each processor fetches a pair of data, multiplies, writes back the data, then one processor will fetch all the data, adds up and writes back. So how many cycles are required for all these operations? So I will wait for say 3-4 minutes or 5 minutes, maybe 3 to 4 minutes. So we are coming to the end of the presentation. So I want all of you to try this out, and if one of you can answer, it will be good. So each processor has to first read a pair of data. Reading one data takes 1 cycle. Each processor had to read 2 data. So then that data has to be multiplied. And once you multiply, the result has to be written back. So all the processors have to do this. But these do this in parallel. One processor need not wait for the other processor. All these reading and multiplication is independent. Then once the result is there, only after the results, all of the results are there, one of the CPU can read the data. So it has to read 4 data. So it has to read 4 data and do sum and then write back. So how many cycles it will take? So how many cycles it will take to complete one multiply operation? Read 2 data, multiply and then write back. Can one of you answer that? Read 2 data, multiply and write the answer back. So all of you are sleeping or what? I don't see any of you responding. So how many cycles it will take? So 1 cycle for reading. You have to read 2 data. 3 cycles for multiply. 1 cycle for writing back. Okay, I think all of you are sleeping. So then I will continue. Okay, so so it should take, sorry, yeah, 1. So for fetching 1, you need 1 cycle. Fetching 5, you need 1 cycle. Multiply 3 cycles. So 3 plus 2, 5. Then the result has to be written back. So 5 plus 1, 6 cycles. So 6 cycles, 6 cycles for completion of one multiplication operation. All the CPUs have to do this, but they have to do it in parallel. After that, one of the CPU has to fetch 3 additional data. Its result is already there. In addition, 3 additional data has to be read back. So which means 6 plus, so 6 plus 3 to read the 3 data, 9, 2 cycles for addition, 11, 1 cycle for writing back, 12. So it is 12 cycles. So I made a mistake. So 12 cycles are required to write back the data. To complete this operation, 12 cycles are required. But if it was a sequential processor, it needed to read 4, write 4, read 8 data, so 8 cycles, multiply 4, multiplication 4 into 3, 12 plus 8, 20 cycles, 1 addition, 22 cycle, write back the data, 123 cycles. So instead of 23 nanoseconds, now it takes only 12 nanoseconds. Okay, so this is how shared memory improves your performance. Okay. So the same thing you can do in distributed memory, but the difference is in distributed memory now you can't directly read and write. You need to communicate between these CPUs for this read and write, which takes more cycles. For example, the communication might take 5 cycles. It's some arbitrary number I am putting, but it might take more cycles, which will reduce the execution time. So this I will leave it for you, how many cycles are required, but the sequence is same. So you read the data. So assume that the data are there in the memory. So 1 and 5 are in this memory, 2 and 6 is in this memory. So you read will take 1 cycle. So 2 cycles to read 1 data, 3 to multiply. So 6 cycles for multiplication. Then communicating 3 data will take another 15. Okay, and then finally the operation. So distributed memory, because of this communication overhead, can be slowed. So what is the advantages and disadvantages? Shared memory have the hardware implementation is very complicated, but it is very easy to use. You just have to use read and write. You have to use store and load to communicate between the data. Load means write to the read from the memory, store, write to the memory. Those instructions can be used to communicate between the processors because the memory is shared. The execution model is simple, it is faster, but the hardware is very complicated. And another thing is you can't scale this well because if you have 100 processors, so let's say 16 processors, all of them have to interact with single memory, which is very difficult to achieve. On the other hand, distributed memory is simple hardware, but data has to be communicated explicitly. It is slower, but it scales well. You can increase the number of processors. Okay, so I will cover one more topic. So that is about shared and distributed processes. But there is one limitation or one important law called Amdahl's law, which limits or which governs this uh, execution in distributed processors or multi-processors. So we are utilizing parallelism in the program or between the tasks to improve the performance. But Amdahl's law states that every program will have some portion which is parallel and some portion which is serial. For example, if in our vector product, if you see, the multiplications are all parallel, but only after all the multiplications are done, addition can be done. So if there was a fifth processor, fifth core, you can't do the addition in that core parallelly because only after multiplication is done, addition can be done. So every program will have parallel operations and serial operations, and these serial operations are going to limit your improvement in performance with the multi-core. Okay, you can so even if you increase the core, only the only those portion of the programs which are parallelizable will improve. The other portion is just going to remain the same. So that is what Amdahl's law says. So I won't go into details because we are running out of time. But when I share this slide, you can actually work this out. The vector product, for example, we were looking at 4 elements. Suppose if there were 1024 elements, and you have more number of cores, how like you can understand that even if you increase the cores, your execution time doesn't becomes half, one third, etc. Or you double the core, you are not going to reduce your execution time by half because the addition operation is always going to be a bottleneck. You have to wait for all the elements to be completed because before doing the addition. Okay, so that is what Amdahl's law is. So so this was the basic multi-core multiprocessor models. There are other models like SIMT, single instruction multiple thread. So in the earlier models, all the processors were operating independently. They were executing separate part of the program. But in GPUs, which use single instruction multiple thread, the same instruction. So this is CPU, single instruction multiple data. So in GPUs, there is something called, so in CPUs, there is something called as single instruction multiple data. The same instruction you operate on multiple data. In the earlier case, we were using multiple instruction, multiple data because each core was operating on different set of instructions, different set of data. CPUs can also support single instruction, multiple data. But in GPUs, you have what is known as single instruction, multiple threads. So there are different threads, but all of them execute the same program. So that is the model in GPU. So they have optimizations in hardware to enable this. So GPU is one of the latest, means it has becoming more powerful than the CPU because more and more parallel programs are being coming into picture, especially with machine learning, etc. GPUs are very good at executing those. One of the most recent model is heterogeneous cores, where instead of having single core, you have these multiple cores, all of them identical. You have multi-core processors, you have GPUs, you have FPGAs, you have different types of processors, all of them connected together and interacting with each other. So we won't go into details of this. So this is one of the latest multiprocessor models because of Again, because of some of the limitations with our transistor scaling technology. So single core, multi-core, heterogeneous processes. So that's how the evolution has been happening. So I'll stop here and wait for questions. If you have any questions, we will answer that. Then we'll stop. So if you have any questions, you can ask now.
If anyone has doubts, just ask the questions to be solved.
I couldn't hear you properly, madam.
If anyone has doubt, just ask.
Yeah, yeah. Can ask. You can ask in the chat window also.
No is there.
Okay, seems like no one has any questions. So either they understood everything or they didn't understand anything, whatever. Sorry for not being able to be in the slide mode because I could use the pen. I prepared the slides based depending on I could use the pen, but that's not possible.
Okay,
Uh,
no problem.
yeah,
Okay, sir, shall I wake up?
yeah, yeah.
Okay, today we had an informative session on multiple process. Sir explained all topics.
Okay.
Microprocessor, that is pipelining, sequential process, parallelism, shared and distributed process, and different topics related to process. Okay, so I'm sure the session was very effective to our students, and I'm thanking this opportunity to express our sincere thanks to Dr. Malesh S. on behalf of CSC Department, College of Engineering, Terangal. Thank you, sir. Thank you very much for your valuable time spent to us.
Yeah. Thank you, madam. Thank you, Oja sir, also to give this opportunity. I
Thank
like interacting with students. Unfortunately, no one is interacting with me, but that's okay. Actually, I didn't get much time to prepare the slides also, and so I thought I'll use the pen to write and. But anyway, that's okay. I'll share the slides with you. Some few
you.
corrections are required, and then I'll share the slides also. You can send it over the students.
Okay, okay, thank you, sir.
Okay. Okay, yeah. If any
Shall
of
I
you
end the
have any
session?
doubts, you can ask. Yeah, just one second. If any of you have any doubts, you can
Okay,
mail me also, nalesh@qsat.ac.in. So we'll wind up. Thank you once more.
okay, okay, thank you, sir.